Okay, today we're going to be studying a new kind of circuit that is, well, it's going to be a combination of both a resistor and a capacitor. And they need to be in series in order for us to study this. So we're going to do two things. One, we're going to study one way where we are charging in our capacitor. Okay. And the other one is going to be when we're discharging it. Okay, so we're going to charge the capacitor the first time, and then we're going to study what happens when we discharge the capacitor. And so we're going to start with our charging. Okay. So in order to charge the capacitor, to get some sort of charge on it, we need to run a potential through it. And so we will take our switch, and this switch right here, if we connect it to this lead, okay, straight across, then we have the battery hooked up to the resistor and the capacitor, and we're going to start building our charge. So then we're going to go for our voltage walk, and we'll start over here, and we go up, and we hit our, as we go across our battery, you know, so if we go up our battery, then we're going to add a certain EMF, right, as we go along our voltage walk. Okay, and we go across here, and then we get to our resistor. Yeah? And our resistor, what's the voltage that we're going to get from our resistor? IR. Okay, it's going to be IR, right? So it's going to be the current going through the resistor at any particular time, okay, times its times that resistance. So that's going to equal IR. Okay, and as this is going, so actually before we get to this next part, let's examine what's going to go on here. If we have a capacitor, what really happens, we don't really get, we sort of get a current, but it doesn't flow circularly through the whole thing. On a capacitor, we're going to start getting an abundance of negative charge on this plate, right? And the battery essentially sucks all of the positive charge out of this side and swings it around and starts to store it on this side. Yeah, so there is a flow of current because we're moving charge from one side to the other. But if we start with the capacitor, the place of the capacitor, it's really it's starting here and ending on the other side, and that's how we get this difference in charge on the capacitor. In order for that to happen, the positive charge has to go through the resistor. Okay, so that's how we get our voltage from the resistor. Yeah? Okay, and this battery acts as a vacuum to suck the charge out this way, and then a pump to push it out that way. It's giving it energy to cause this to happen. Okay, so it doesn't flow, okay, but while the capacitor is charging, there is a shift in our charge going through. We have in the past pretended that it happened instantaneously, yes, but that's primarily because we didn't have anything resisting the flow of the charge. Well, now we do. Okay, and with this resistor on there now, it's not allowing for an instantaneous charge of the capacitor. It's going to slow it down a little bit. And so, I'm sorry?
Why would you want to do that?
There are a number of purposes of it. Sometimes you don't want a capacitor to be fully charged, fully discharged instantaneously. You want to build the charge. And then, for example, flash bulbs, electronic flash bulbs on cameras. Okay, you don't want, they run on a capacitor, and so they flash, and then in fact, you can hear it sometimes on certain, if you hear certain flashes, you hear this, you get the flash, and you can actually hear the charge. Okay, yeah, it's charging the capacitor, right? You don't want it to happen instantaneously because you want to give the capacitor time to allow the light bulb to cool down. All right, because otherwise, if it's flash, 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 if you're repeating flashing, the light bulb will burn itself out too quickly. It needs time to be able to reset. Okay, so it is intended to be a delay system for the charge of the capacitor. All right. So this is going to be our voltage drop, right? Because our current our current is going to go in this direction. Okay, this is the flow of charge is in this direction around our current. So if we're going this way, if we're increasing our voltage here, we get to this resistor, and this is a voltage drop as we go across that resistor. Down here to the capacitor, however, we have another voltage drop, right? Because we're going to do a full walk around our circuit, we're going to lose some voltage here for the capacitor. And what is that going to be? What do we know? Okay, that Q equals CV, right? So our voltage then is going to be Q over C. Equals our voltage. So the voltage drop as we cross our capacitor is going to equal Q over C. And as we go around our whole circuit, okay, now that we've completed our circuit, our total voltage is now what? According to the loop rule, as we go around, the total voltage change is 0, right? We have a 0 there. Okay, well, what's that? Current. How is current defined? Okay, it's a coulomb per second, right? Is there a differential?
Yes.
Okay, I equals dq dt, right? Ah, so let's plug that in for I. All of a sudden we're going to get our voltage we're good?
Yeah.
Okay. Okay, and I'm going to change this to lowercase q just to be consistent. So now this still equals 0. So now look what we have. We have a differential equation. Good times. All right, we have a differential equation that is dealing with our voltage here, and it's in units of charge. So it's in charge in units of time, right? So, and so what we're going to start finding here is that it takes a certain amount of time to charge up our capacitor, and that's really what this equation is used to find. So what happens when our well, let's go back for a sec. Let's keep going with this. Let's get dq dt by itself. So to get this by itself, we're going to get we would divide everything by r, right? Okay, so we were going to get er minus dq dt minus q over rc equals 0. Okay, so take a look at this equation here. If these all equal 0, if this minus that all equals 0, this is in terms of current, right? Well, if this is in terms of current, don't these also have to be in terms of current? Okay, so here's a pretty mind-blowing concept here. Voltage divided by resistance, okay, we know that I equals V over R. We're, Ohm's law, I equals V over R, we're cool with that, right? Check this one out. Here's Q divided by RC. Resistance times capacitance gives us what unit? It gives us seconds. An ohm times a farad, okay, is 1 second. Okay, an ohm is a what? Yeah, ta-da, thank you very much. Okay. Resistance is what? Resistance is a volt per amp, right? Shh. Okay, well, an amp is really a coulomb per second. Yeah? And a capacitor is coulomb per volt. So we're left with 1 over seconds, which equals seconds. Okay, and this actually, this concept of RC actually gives us, it's a new value of time. This right here is called, it is called new time. Okay, it is called the time constant. Okay, it is the time constant for this particular pairing. Okay, and the time constant has a variable tau. Okay, not to be confused with torque. Torque, not torque. Torque. Okay, or not Tupac either. No. 2 pi. No, not that tau either. Okay, yes, I'm aware of that tau as well.
But why? I mean, is that just second?
Okay. Yes, it is just seconds, but it is a particular amount of seconds, guys. It's a particular number of seconds. Okay, that is specific. So, yes, it has units of time. It's sort of like a frequency, having units of 1 over time.
So do we write tau s or just tau?
Just tau. Okay. No, the tau is this value. It is r times c. Okay. We're not going to use. And we can find tau in other places, and the concept of tau has other uses. We're not going to use it that much, although you will see RC working together quite a bit in the math that we're going to do. Now, so take a look at this. What happens if we're going to charge this circuit? What is going to be our current, okay, when t equals 0? Right, well, at the instant we connect the circuit, what our amount of current is going to be, well, this becomes 0, right?
Yeah.
Okay, at the very beginning. Okay, and this, we don't have any resistance or capacitance yet because we don't have any charge or anything getting there yet. So, our E over R is equal to, this is our current at time equals 0, is this E over R. Okay, so when we have, we initially charge something and you want to look what the original current is, it's E over R to start with. Okay, but that's just the Ohm's law, straight up with that. Now, let's solve for Q here. We're going to rearrange this to get dq by itself. We're going to arrange this to get dq by itself. Okay, dq equals E over R minus Q over RC. Yeah?
Is it? Yeah.
Okay. We want to combine these into one equation, so that's going to equal CE, okay, minus Q all over RC. You guys with me there?
Yes.
Okay. And this equals our dq dt.
At any time?
Well, we're still solving for Q here. So, all right, so we keep going with the math, and we're going to move our, we're going to, all right, am I getting this right? Yes. Okay, so we're actually going to switch this up a little bit, and we're going to get dq over CE minus Q is going to equal dt over RC. Yeah? We just kind of did this to the proportion, right? So they were here, and we went like that. Okay. And then we're going to integrate, because that's what we do. So
There you go.
Actually, hold on a sec. I'm gonna rewrite this because it actually makes the integral easier, and I had to look this up on our table of integrals, and so I had to flip it around. So this actually becomes dq over q minus c e equals negative dt over rc. Follow me there? Okay, I flipped this around to get the negative on this side, and you'll see why in a bit. So then we integrate this from 0 to q, and yes, I don't want to hear about, oh, you're not supposed to do that, because I'm doing it.
You're supposed to do that.
You're not supposed to use the same variable here that you use here. You should use something else, but the math still works. So it's an esoteric argument.
Bring this to Supreme Court.
All right, this brings us to oh, yeah.
Hello. Talk show folks.
Okay, you guys with? Okay, I don't feel like doing all of this. You guys can work it out if you want.
Wait.
Okay, this is what it comes out to. Okay. So we get here. Now let me finish my notes here. So how do we get rid of the natural log? Right, we turn it into an exponential equation. So this becomes q okay, and we'll keep solving to get it down to q. So q minus c e equals
There is.
I put it back. Found it. There it is.
We should have captured that. Oh. Put some caption on it.
All right.
Q minus C.
Okay, and then we're going to add CE to both sides.
Really complex.
All right. And I'm going to skip a step here, but this is going to become CE 1 minus e to the negative t RC. And let's take a look at this.
Reminds me of AP.
Reminds you of AP Chem?
Yeah.
Yeah, there are many, 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 many applications of the exponential function. Okay, interest is an exponential function. Okay, decay is a many kinds of decays are.
Like CE, KT.
What's that?
Like CE to the KT, was it?
I screwed up on that.
CE to the KT.
Yeah, it reminds me something like.
Yeah, that's exactly what it is.
What?
It's pretty close. Okay, it's the same idea. So, here's what I want you guys to look at. We're going to create a graph here. Of Q versus T. All right. If what if T were 0? What is our charge going to be if time equals 0? No. Wait a second. Oh yeah, you're right. No, I'm sorry. I'm sorry. Yeah, so we'll equal 0. Duh. Okay. Sorry. Yeah, I broke math. Yes, it will equal 0. So at time equals 0,
Let's prove it.
we're here. Right? What is the maximum possible value that Q can actually be? Okay. This cannot possibly get any larger than 1, right? This term will approach 0 as t approaches infinity.
That's right.
Yes? So, that creates for us a maximum charge of CE, which should make sense. Okay, what's the charge on our capacitor? Okay, it's capacitance times the voltage, right? So the capacitor should charge to its maximum possible, charge at our voltage times as time approaches infinity, right? So we create this. We create this exponential function that asymptotes at C over E. Okay. The concept of this is somewhat similar to a bell curve in statistics. That you never, if you have a large enough sample, statistically, you take a population, but you don't want to leave it as a population. You want to extrapolate if it was an infinite number of subjects or infinite number of data points. And so you never get to the end of your bell curve. It asymptotes at 0, okay, on your bell curve. Well, same idea here, that we never quite get here, although we all know that for all intents and purposes, because charges are quantized, guys, your other conversation is really distracting again. Because charge is quantized, because we have individual fundamental particles of charge, we will eventually get to our max charge. Okay? And it's sometime down the line. But if you really wanted to get down to the per unit charge, we could do that, but I don't want to deal with that. Okay? We just know that after a certain amount of time, you're going to get 99.99% of your charge. It'll essentially be full. But here's the interesting thing. If we use RC right here, let time equal tau. Let it equal this RC constant. This becomes -1, right? And so we call this time constant to establish, to get rid of this exponent here. And this becomes 1 minus 1 over e. Yeah? Okay, that winds up being right about here. Okay, that's tau. Okay, which equals our time constant. And this is about, tau makes this about 0.632. So at this point we get about 0.632 of CE at time tau. Okay, that means that we're about 63% charged after a tau. And then if we go another tau, then we would be, all right, so we'd be out here. Okay, and we'd be another percentage higher, but this would be e to e squared, right? And then e cubed if we do another tau. That makes sense, you guys? Okay. So it'd be 1 over e, and then 1 over e squared, and 1 over e cubed, and 1 over, and so that will eventually, 1 over e to the infinity is going to become 0, and so we'll eventually get to our CE. Okay. What is the current going to be of this, though? So now let's work back. Q what is what saying?
That's an arrow.
It's just an arrow.
Gosh, you're picky.
Okay, if you pay attention to what I'm doing rather than, okay, you'll see that I just throw an arrow rather than a lambda. So don't worry so much about writing it on the paper right now. Watch this and fill in the blanks with the video. Okay? So, So find dq dt. Okay, well, this is just going to go to 1, right? All right, the CE times 1, that's going to become 0, right? But CE times all of this is going to become, the negative cancels with negative, so we're going to get CE over RC using the chain rule. You follow that? Okay, the negative 1 over RC is going to multiply out here by the CE, and by that negative making it positive. But then those cancel, and all of a sudden we have units of E over R, which is current again, right? So our current for any particular time, okay, is going to be E over R, E to the T over tau, negative T over tau. Are you with me so far? Okay. Let's graph this one. So this is now current, and that's time. Okay, do we have a maximum current? What's the value? E over R, right? If this thing goes to, this can only be 1 or less, right? Okay, so if this is 1, then this is going to be E over R. Is our maximum current. Okay, but then where does the curve go? Yeah. Okay, so our curve is going to go in that direction. And we're going to have, at time tau, okay, equals RC. Okay, this winds up being, ironically, it's 1 minus that, right? Because I'm sorry. It winds up being 1 minus this. Okay, so 1 minus that is just, so it's going to be 36.8%. Okay, so our current at time tau is 0.368 of our max. Okay. Now, take a look at these graphs. Okay, first of all, if you take your magic left hand to slope, okay, you go like that, it's going to be, it is going to decrease at a certain rate where its maximum slope is here, right? And we curve like that as we go along. Well, that means we're starting high, and then we're decreasing all the way to 0 slope, yeah?
Yeah.
Well, we're starting here. Okay, well, but that's this path, right? This is decreasing to 0, right? Because this is, imagine this was position, this was velocity, right? So this would be, the slope would be decreasing to 0. Well, what does this do? It decreases to 0, yeah? It also makes sense because if your charge is increasing, is this somebody trying to get in? Okay. If the charge is increasing, okay, we're going to increase to a certain maximum charge, right? Which means that we're going to get most of our flow to begin with because there's not going to be a reverse potential from the capacitor, right? We're not getting something pushing back, from our separation of charge. And so the rate at which we're able to put charge on that capacitor is going to decrease as the charge that goes onto the capacitor is increasing. Yeah? And the rate at which it is decreasing is dependent upon the amount of charge that's on there. And this happens a lot, that the rate of something happening depends on how much you have. Yeah? Whenever you have that, in any course in any application, you're going to get an exponential function. That when the rate of something is changing depends on the amount of stuff of that something you have, that becomes an exponential function that uses this e, that uses the natural log in the e. Okay, so that is charging our RC circuit. Okay. Good so far? Okay, we're going to change our switch. And now we disconnect the battery. Yeah? Disconnect the battery and we close it like that. So now the only thing we have is the resistor and the capacitor. Okay. All right. So, new page. Now we just have, let me see if I can make it, I'll just do it with the pencil here. So we're going to discharge. That's just not dark enough. I don't like it. So now we're going to discharge our capacitor. We need to draw, so now we're going to draw the other half of that switch. So we had R and C. When we begin to discharge, how much charge did we have on our capacitor? Oh, this is still E. Okay, our Q max, okay, which is the maximum charge we had, was equal to what? Was equal to, our maximum charge was equal to CE, right? Okay, so Q max equals CE. So, for a discharge, at time equals 0, Q equals Q max. Yeah? That we're starting with all of our energy stored up on our capacitor. So we go around our loop, and what we had before was E minus IR minus Q over C equals 0, right? But we don't have a voltage anymore. So it's just IR minus QC. Justin.
You said earlier that when you flip the switch and disconnect the battery.
Yes.
Is the switching of the switch connected to disconnect the battery as well, or is it two separate things?
We flip the switch from here to here in order to disconnect the battery. Okay. All right. So this, mercifully, looks like a much easier differential equation. Okay, so this one I can do. All right. Okay. So now we get this. All right, we move the Q to these Q over C to the other side, and we divide by negative R, and we get that. Nick. Okay. All right. So then we're going to flip this around, and we're going to get this to become dq over q equals negative dt over rc. Yeah? Okay, so we can integrate this. Now, what is the integration of this going to be? Our integration is going to be okay, well, at time 0 is where we start, and we'll go to whatever t we finish with.
Just constant?
Okay, no, this is our final t. This is, okay. But what's happening over here? What charge are we starting at?
0. No. CE.
We're starting at Q max. Or, well, I'm just going to call it Q. Okay, I'm going to call it big Q right now.
So Q max.
Okay, it does equal CE.
Oh.
It does equal CE, but we're going to call it big Q because I don't want to write more than one variable. Okay, to Q. Just as we went from 0 to Q before, now we're going from Q max. We're starting from a high charge to a diminishing charge. Okay, integrate both of these. We're going to get ln Q over Q equals negative T over RC. And let's solve from here. So we're going to put this into an exponential. And I'm just going to skip a couple steps here. So we've done this math before, but this is Q equals big Q e to the negative T over RC. Yeah? Oh. So Q equals Q max e to the negative T over RC. This should make sense to you guys. Okay, that at time equals 0, E equals 1, we're at Q max. As T progresses, this value starts to decrease. This value starts to decrease until there is no charge on the capacitor. It will essentially, the charge will leak away from the capacitor if we detach it from a battery. Yeah? Okay. So we graph these. I've always found it funny that as soon as you draw a first derivative graph and you draw something below, you know there's going to be something negative. Otherwise, why add the other quadrant to it? It's all okay. Okay. So here we're going to have our Q max, right? That's Q, and as it discharges, it's an exponential discharge. And now here's the interesting thing. If this is our charge distribution on our capacitor, what's going to be the direction of the charge flow? It's going to go backwards. It's going to return all these positive charges when it get back over here and cancel the negatives. Yeah? Or, okay, if it's easier for some of you, Nick, here's where all the electrons are, right? Okay? So our charge carriers are going to move back where they're going to move against the positive electric field, right? They're going to move back towards all the positive charges, right? They want to get back, they want to get with you, right? They want to get back together. Okay, so they're going to flow back around, but if it's a negative charge flowing in the clockwise direction, that means actual current is going back, which was opposite to the direction we established when we attached the battery. It's going to flow opposite to the direction of the potential of the battery. So our current now is not up here. Our current is going to start in the negative direction and then slow to 0. Okay.
Is it asymptotical on the?
It is asymptotical.
Vertical, or is it?
Well, no, it crosses.
What point?
And the current, so if we do dq dt again, this becomes okay, so our initial current is this. Negative Q over RC. Okay, and here's where our time constant comes in. By the way, it's Q over tau. Our initial current is negative Q, our total charge, divided by tau.
So tau doesn't change in any.
Tau is a constant of the system. It is
Oh, it's given.
well, sort of. It's tau is derived from the product of the resistor and the capacitor, and so it is a characteristic of the circuit that you're dealing with. Okay, and so here, here's your tau, and here's your tau. All right, those are your RC circuits, and so I recommend that you guys get used to those equations. That in particular, this equation here, guys, get used to this one because you can derive all of them from this.
Wait, what?
Okay. So what's that?
So you set up the tau. What is the y value if you plug in tau? It becomes.
Okay. Well, if you plug in tau for time, it becomes
Negative Q over RC.
negative Q over ERC. Yeah.
ERC.
ERCE, whichever.
So the tau from one circuit isn't necessarily the same as the tau from another circuit?
Right. It's think of it as the circuit constant. Okay. It describes the nature of the circuit. All right. And that is all.